change, we have this ft equal to 1. This is in time domain. Ft equal to a equal to 1. But in Laplace domain, it is f bar a is equal to 1 by s. See, Laplace transform of ft we are denoting by f bar s. In time domain, it is ft, and in Laplace domain, it is f bar s. So with this notation, if we consider a unit step change, then in time domain we can write ft equal to a equal to 1. The respective Laplace, in Laplace domain we can write f bar is equal to 1 by s. Fine. So this is step input, this is unit step input, and this is a typical example. It's very simple thing. Your steam valve is at a fixed opening, that is steady state. Now suddenly we are increasing or decreasing the valve opening, and we are remaining there. This is the example of step input. I repeat, one valve is there, I mean one pipe is there, and definitely one valve is fitted there. Initially the valve is at fixed position with a certain opening that corresponds to steady state. Now suddenly we are changing this valve opening. We may increase or decrease anything, and we are keeping that valve opening there for the rest of the time. This is the example of step change. Next, come to another step change, that is rectangular pulse function. This is the graphical representation of rectangular pulse function. This is the rectangular pulse function. When t is less than 0, our function equals 0. And the time is in between 0 to b, our function equals a. And again we are coming back to the original location, original position, and t is greater than b. That means when t is greater than b, our function is equal to again 0. So you see, this is basically a combination of two step changes. One step change is from here to here, we are increasing, and another step change is we can start from here and decreasing. I repeat, this is basically the combination of two step changes. In one step change, there is an increase. So from 0 to a, we are increasing. And in the second step change, we are simply decreasing. That means we can start from here and we are decreasing. Fine. So sometimes it is written as two consecutive step changes. Sometimes two consecutive step changes are introduced in the load variable. This is a rectangular pulse function. So based on this concept, I can divide this. You see how it is divided? This is the first one, as I mentioned. First step function, which we are representing by F1 now. It is 0 when t is less than 0. And this F1t is equal to a when t is greater than 0. And we are considering this part of step change. We are considering the first part of step increase. You see, this is step increase basically. In a similar fashion, we can consider the next part like this, you see. Second step function is like this. See, here we are considering this, the top branch, as 0. We are starting from 0 to a basically. This is a step decrease. Second part is basically the step decrease. First part is the step increase. So direction wise they are opposite to each other. Direction wise F1 and F2 are opposite to each other. Okay. In fact, I can write therefore this one as F1t minus b, and one minus sign is there. Can I write this minus F1t minus b, student?
Sir, if we writing this, there should be minus a, or
Which minus a?
the second step function at the, it is decreasing from 0. So
Yeah,
then if a is positive, then it should be minus a.
that's why minus a is written. I mean minus sign is written here.
So where you write, where you have written t
T
greater than b,
minus, yeah,
where t is greater than b, it's a. It should be minus a because
that's
it
why
is
minus sign
decreasing.
is here. We are considering this is a 0 and this is a, no?
Yes.
So that's why minus sign is here, no?
Okay, sir.
Okay. Now can you find the, you see I have written like this form. Ft equal to F1t plus F2t. And it means F1t minus F1t minus b.
Sir,
Yes.
sir, then if f2 of t is minus f1 of t minus b, then a should, when t is less than b, then it should be a, or and when t greater than b, it should be 0, right?
Yeah.
Sir, but here it is reverse.
So that's why minus sign I have given here. No, it is reverse. See, you understand like this way. This is 0, this is a. Fine. So you are
Yes, sir.
saying it is minus a. You want to
No,
consider
sir,
here
not minus a. Like if t is less than b, then it should be a, right?
t is less than b, it
Uh,
should be 0. We are considering 0 here, no? and this is minus a. We are considering this is 0 and this is minus a. What is indicated here?
Okay, sir.
And this one is quite obvious, t minus b. Here you can put suppose anything, any variable, say capital T. So this is capital T. Yeah, now can you tell me what is the Laplace transform of this ft? I mean, I am asking the expression for a bar within bracket s. Can you find it and let me know? My question is now to find the Laplace transform of this ft. I mean, let me know the expression for f bar s.
A by s of 1 minus e power minus bs.
A by
S into 1 minus e power minus bs.
how you are getting b? Oh, that b. One again tell a by s minus
A by s of 1 minus e power minus bs.
within bracket you were saying.
Yes, sir.
Yes, correct. What's your roll number?
19ch10065.
Yes. If you have finished this one, now can you find the expression for unit rectangular pulse change? Unit rectangular pulse change. Anyone else got the answer?
So 1 by s into 1 minus e to the power minus bs.
1 by s into
1 minus e to the power minus bs.
what is this? Pulse or
Un-
unit pulse?
Unit pulse. I am taking a equals 1 in the Laplace transform.
No, no. It's not really the expression. Let us first listen. All of you got the Laplace transform of this ft 3008 j 3008 30018 Pratik 30018 Pratik, you got the answer. Shibam Raj.
The 30018 is Vardhan.
30018 is?
Is Vardhan, not Pratik.
No, 30012 I told.
Okay.
Yeah, 30018. Your Bardhan.
Vardhan, sir. Yes, Vardhan.
Sammukh Sai is written.
Yes, sir.
Is
Shanmukh
the
Sai
same
Vardhan.
person? Oh, okay.
Yes.
Oh, it is not there in the ERP. ... 7. Anyway, fine. You got the answer?
I'm trying, sir.
Okay, do it. See, Laplace transform of this one is very simple, I think. Let me ask a couple of more students. 10060, Saheb, Nazir. 10060. 10061, Tridipta Das.
Yes, sir.
Yeah, you got the Laplace transform of this ft, what I am showing. tell us how you got it.
A by S minus in bracket.
No, you
1
tell
by
us how you get. I'm not asking the answer. What is the Laplace transform of this one, F1t?
A by S.
Okay, what about this one?
1 by S square minus B by S.
1 by B square, A square or S square?
S square.
Check this one. The Laplace transform of just this one, you check. One 0063. 10063 Udaya Mishra. 10062 Anuradha. 62 Anuradha. 64 Utkars. 66 Chinmay Jain.
Yes, sir. Yes, sir.
You got the answer?
Yes, sir.
Tell.
It is A by S into 1 minus E with the power of minus BS.
You tell what is the transfer function of this?
So
Laplace
F1 is
transform.
A by S,
This one.
F1t, and this is e to the power minus BS by S.
E to the power minus BS by S. A is not there?
Yes, sir. A is also there, sir.
You were
So
Chinmay, no?
A by S into e ki power minus BS.
Okay. You were Chinmay?
Chinmay Jain.
Okay, good. Fine, this one is answer. You see, it's quite straightforward to find.
Sir, I told you the same answer.
What's your roll number?
CH 19CH 10051.
10051.
Yes, sir.
Subham Kumar.
Yes, sir.
Okay. I have noted that, Subham. Don't worry.
Thank you, sir.
Yeah, next come to the unit pulse. So concept of unit pulse is, you know, its area is 1. Fine, you see. Okay, whenever we are coming to this type of structure like rectangle, square, we need to make the area 1. So here we have changed, I think, in place of B, 1 by A is considered. Oh, it was yeah. So this was B, no? So here we are considering B equal to A, and this one is 1 by A. Okay. So can anyone tell any physical example of this rectangular pulse function? Anyone? Any practical example or physical example of this rectangular pulse function? I have given one example for step function. So it is just the combination of two step functions I mentioned before. Accordingly, do you have any answer? Do you have any example for rectangular pulse function? Anyone?
So you open the stream valve for a certain amount of time and then you turn it back to the initial position.
For the same pipeline you were saying?
Yes, sir, for the same
Yeah.
pipeline.
Yeah. Roll number?
So 30036.
Yes. So earlier we have considered, we have increased the opening or decreased our opening and we remain there, but here we are coming back. So I did not write anywhere example. Okay. So steam valve or for a pipeline, the valve opening is fixed at the beginning. Okay, so that indicates the steady state. Then suddenly we are increasing the valve opening, staying there for some times and coming back to the earlier valve position or steam position, it is better to say. I repeat, initially suppose the valve opening is 50%. So that is steady state. Now suddenly we are increasing the valve opening to 60%, suppose. 10% we are increasing. And at that 60%, with that 60% valve opening, we are staying for some times. Then we are coming back to again 50% opening. So we are decreasing 10% opening. Okay. So this is the example of rectangular pulse. Now come to impulse function. See here you note down that this unit pulse function we are representing by del suffix a. Unit pulse function we are representing by del suffix a. Okay, because this notation we will use in our subsequent study. Now this is the impulse function, you see. First, the unit impulse function is shown. Initially, the unit impulse function is shown here, which is also called as Dirac function. So you draw both the figures. I mentioned that the unit pulse function we are representing by del suffix a. Okay. Now when this duration is approaching to 0, I mean when a is approaching to 0, naturally it is closing to infinity. So this is unit impulse function. Okay. Now you come to this portion. So we are representing this del. We are representing our unit impulse function by del. So del is basically, you see, limit a tends to 0, del at. This a is coming closer to 0. So we can write this one accordingly. Limit a tends to 0, del at t. Now if you take the Laplace transform, then we can write accordingly this. Yeah, although I have shown what value you are getting finally. Laplace transform of Dirac function.
Sir, 1.
How you are getting this one?
So take limit of the finals at the final step, which is limit a tends to 0 of 1 minus e power minus as by as. So then we can expand. We can expand or either use the L'Hopital rule to get the limit when a tends to 0.
Which rule?
Sir, where you L'Hopital rule where you divide, where you differentiate the numerator and
Yeah.
denominator.
What's your roll number?
Sir, 30036.
Yeah, correct. Yale Hospital rule, I think you were saying, no?
Yes, sir.
Yeah. So if we use Yale Hospital's rule, I mean what he told, that is correct. Differentiation of these two, limit a tends to 0. Differentiation of these two, we get finally 1, which is called Yale Hospital's rule. I think you all know that. Okay. Now if you consider any area, then it is this. Yeah. This is the example. Next, we will come to another function that is called ramp function. Okay, so ramp function is represented by this. This is a graphical representation. This is a graphical representation for ramp function. So obviously you are understanding why this is called ramp, and it's a straight line. So Laplace transform is a by a square. So where this type of function we experience, do you have any chemical engineering example where we have this type of ramp change, especially in practical scenario?
When we open the valve slowly, the amount of flow linearly increases.
Yes, in fact, it's not even slowly. If you open the valve, keep on increasing the valve or keep on decreasing the valve, we experience this type of change. Okay, and so what are these two? These two straight lines. If you consider this example, what these two straight or horizontal lines indicate? These are basically,
steady states.
Usually these are upper and lower limits. Definitely, you can change from 50 to 60% also. You can have this type of change. But typically, if you consider this as 0% opening, this as 100% opening, so these are basically the limits of the pipe. Got it? This indicates, this is the lower bound, basically lower bound, which indicates 0% opening, and this is the upper bound that indicates 100% opening. 0% opening and 100% opening. But as I mentioned, you may also consider this as 50% and 60% opening. That is also possible. Okay, but this typical figure we will discuss when we consider the controller. So we have considered, total 4 types of forcing functions. Okay, step, then pulse, then impulse, then ramp. And apart from these, we can have also like sinusoidal wave. That type of forcing function also we may face in practice, or even not so systematic like sinusoidal wave. Okay, but for theoretical investigation, usually these type of forcing functions are considered. Step input, pulse, impulse, ramp, and sinusoidal wave. So this is all about our input functions. Yeah, so still we have time. I can go to next topics, or did you get the answer of these questions, students? Or you did not try? Vardhan?
Yes, sir. Sir, I'm still confused why, like, about the first question. Like, why there is energy balance not considered. That day we've asked in the class also.
Okay. So answer of other questions you got?
Yes,
or
sir.
That?
Yes, sir.
Okay. Good. Anyone got the answer of the first question? Tanmoy?
No, sir, I didn't get it. Why we
Or,
ignored energy balance?
or you did not try it?
Yeah, I thought about it, but I'm still not getting it. That why we ignored the energy balance in the distillation column.
Okay. Anyone else?
I'm not sure if this is the answer, but when I thought about it, I think the energy balance equations are baked into our assumptions. When we made our assumptions, they kind of take care of the energy balance part on their own.
Which assumption?
The assumptions that we started with, all of the assumptions together, they take care of the energy balance.
Oh, okay. Not really. Yeah, in that sense, you can tell we are not considering, means definitely it is not valid for our example system. Your answer is something like that, no? We did not consider means if our derivation, equations, everything is correct. Definitely, our case is not, energy balance is not really applicable to our example system. Basically, I want very specific answer. You see, the general.
So when we had that point that
Your voice
when
is
the
weak.
vapor, so like in assumptions we are considering.
Yeah,
Hello?
till now. Yeah, till now.
Yes, sir. So when we assume that the same amount of vapor and liquid are condensing and vaporizing, we are essentially using an energy balance.
Your voice is breaking. Anyway, I think you indicated to say that since we are considering equimolar overflow, 1 mole of condensing vapor releasing enough heat to produce 1 mole of enough heat to vaporize 1 mole of liquid. I think you were saying that. Yeah. It is somewhat right. You told
Yes,
that.
I was
No?
saying that.
Yeah, yeah.
Yes, sir. Yes, sir.
Yeah. It's I think correct. In some sense, it is okay. What's your roll number?
So 19CH10037.
Yeah, in some sense, it is correct.
But still, sir, there should be some energy balance at condenser and reboiler, right?
Why? Oh, that we have neglected, no? Thermal balance, you were saying, no? Thermal balance, you were saying.
Yes, sir.
Yeah, that we have neglected. That is basically heat exchanger model. Yeah, that also we can consider, no problem. But this is mainly specific to the tower, this energy balance equations.
Okay, sir. I was
But,
thinking that it also includes both reboiler and condenser.
no, it's not really. That one assumption is there. You see, thermal dynamics we are neglecting. But definitely, if we want to make the model more rigorous, more accurate, we can also consider that. And that is nothing but a heat exchanger. Okay, that we can also consider. One indication I can give you, although you did not study your mass transfer course, that relative volatility alpha, no? Alpha is basically function of temperature and pressure. Okay. I think you can give, you can understand also this point. Yeah. See, if you see this equation, suppose let us talk about this Ki. Okay. Let us talk about this Ki. Ki equal to Yi by Xi. Can you tell me how we calculate Yi? This you know. See, you forget about this distillation modeling now. You just think like this way, there is a vapor and liquid. How we calculate the vapor composition? I think you have started in your process calculation. How we calculate X for a ideal mixture? Anyone? Okay, let me ask then in a different way. What is Raoult's law? Anyone can tell? Yeah, I think you know Sankalp. Sankalp Bose 10045. What is Raoult's law? Anyway, you think this Raoult's law, and this Raoult's law is used to calculate Xi for ideal mixture, and you see the Dalton's law, which is used to find Y for vapor mixture, and you will see that this both, you know, This is basically equal to function of pressure and temperature. This Ki equal to basically function of total pressure and temperature. So if that is the case, alpha I is basically function of pressure and temperature. Now, if we consider alpha constant, and if we consider our pressure is constant, naturally temperature is constant. This is another answer. If temperature is constant, there is no need of any energy balance equation. Got? I repeat, alpha ij we have considered constant value. Now alpha ij is function of pressure and temperature. Now our column pressure is fixed. So naturally temperature is fixed. If temperature is fixed, there is no need of any energy balance equation. Energy balance equation basically calculates temperature. Okay, this is another answer. Okay, fine then. Thank you, students. We'll meet you tomorrow again.
Thank you, sir.
Thank you to everyone.